In the dark skies above the Chilean Andes, a machine is watching. Every night it looks at the heavens with an eye so vast and so sensitive that it can see things no human has ever seen before. And what it's revealing is both extraordinary and unsettling. Out there in the cold of space, objects are spinning so fast they should tear themselves apart. Asteroids the size of mountains are careening through the solar system on trajectories we never knew existed. Distant worlds are hiding in the deep outer reaches of our cosmic neighborhood, waiting to be found. The Vera C. Rubin Observatory has just opened its eyes. And in doing so, it's shown us that we've been nearly blind to the universe spinning all around us. This is not a story about a new telescope finding distant galaxies or ancient light from the far reaches of space. Well, it does that too. But more urgently, it's about what Rubin is revealing to us about our own backyard, the solar system we live in. It's about the scale of cosmic violence and motion that surrounds us, hidden from view. And it's about what happens when we finally develop a machine with the power to see it all. For more than 20 years, scientists dreamed of building Rubin. They imagined a telescope that could do something no other telescope had ever done. Sweep the entire sky visible from one hemisphere over and over again, night after night, for 10 years straight. They imagined a camera so large it could capture an area of sky the size of 60 full moons in a single shot. They imagined a system so fast, so sensitive, that it could detect changes happening in the universe, asteroids moving, stars exploding, galaxies transforming, and alert the world's astronomers in real time, minute by minute. In 2024, that dream became real. Perched at nearly 9,000 feet on Cerro Pachon in the Atacama Desert of Chile, engineers and scientists began activating the Vera C. Rubin Observatory. The main instrument is an 8.4-meter telescope, about as wide as a tennis court, coupled with the largest digital camera ever constructed. This is no small upgrade from previous instruments. The camera contains 3.2 billion pixels. To put that in perspective, the highest resolution commercial camera you can buy for a smartphone is maybe 100 million pixels. The LSST camera, the Legacy Survey of Space and Time camera, has 30 times more pixels than that. It's so large that inside the camera, there are hundreds of sensors arranged in a special pattern and data flows through this instrument at a rate that rivals major internet bandwidth hubs. When the Rubin Observatory released its first images to the world on June 23, 2025, astronomers were stunned. In just over 10 hours of test observations and just several nights of commissioning work, Rubin had captured millions of galaxies and thousands of asteroids that had never been seen before. But no one was quite prepared for what came next. As teams of scientists began analyzing the early data more carefully, they started submitting discoveries to the International Astronomical Union, and they kept submitting, and they kept submitting. By late spring of 2026, the final count became clear. In its early optimization surveys, spanning only about 6 weeks of observations, the Vera Rubin Observatory had detected over 11,000 previously unknown asteroids. 11,000 in 6 weeks. Most telescopes in the history of astronomy had discovered asteroids in the hundreds or maybe the low thousands over entire decades of observation. Rubin was doing it in weeks, but the sheer numbers weren't even the strangest part of what Rubin was seeing. Among those thousands of asteroids, astronomers noticed something profoundly unusual. Some of them were spinning, not slowly the way normal asteroids spin, taking hours or even days to complete one rotation. These asteroids were spinning so fast they seemed to violate the laws of physics. The fastest of them all is an object designated 2025 MN45. This asteroid is 710 meters across. That's nearly 3/4 of a kilometer. To visualize it, imagine an object larger than some mountains, larger than the tallest skyscrapers on Earth stacked on top of each other. Now imagine that this enormous hunk of rock is spinning so fast that it completes a full rotation every single minute. Not 1 hour, not 10 minutes, 1 minute and 58 seconds. That means if you were standing on the equator of this asteroid, you'd be traveling at a speed of over 600 kilometers per hour, faster than the fastest race car, all around. When scientists ran the numbers, they realized something that shouldn't be possible. According to physics, an object made of loose rubble should fly apart if it spins that fast. Asteroids, we always thought, were essentially piles of rock and dust held together only by their own gravity. Spin them too fast, and gravity can't hold the pieces in place anymore. They should scatter into space like a spinning wet dog shaking itself dry. Yet there it was. 2025. MN45 wasn't just holding together, it was one of 19 similarly extreme fast spinners that Rubin detected. There was 2025 MJ31, rotating every 90 seconds. There was 2025 MK41, spinning once every 3.8 minutes. For 2025 MN45 to survive this rotation, for it to not tear itself to shreds, it would need to be made of something almost as hard as solid rock. it would need to be almost monolithic. Scientists now suspect that this asteroid might be either a remnant of something much larger that was shattered in an ancient cosmic collision, or the survivor of some catastrophic impact that left only the densest core intact. These weren't distant theoretical discoveries. These were real objects in our solar system, spinning in ways we'd never imagined possible, revealed to us for the first time by Rubin's unprecedented sensitivity. But the discoveries extended far beyond our immediate neighborhood. Rubin detected 33 previously unknown near-Earth objects, asteroids that orbit close enough to Earth to potentially pose a threat, though scientists are quick to emphasize that none of the newly discovered ones pose an immediate danger. What was remarkable was the sheer variety and number. Some of these near-Earth asteroids are hundreds of meters across. These are the kind of objects that, if they ever collided with Earth, would cause regional devastation. They would trigger earthquakes, tsunamis, and dark skies from dust and debris. They wouldn't end civilization the way a dinosaur killer asteroid would, but they would transform the landscape of wherever they struck. Scientists estimate that only about 4 in 10 asteroids of this size have been discovered so far. They're lurking in the solar system, invisible to older, less powerful telescopes. But Rubin can see them. And as Rubin continues its 10-year mission, scientists predict it will discover nearly 90,000 more near-Earth objects. Some, perhaps many, of those will likely be potentially hazardous. For the first time in human history, we might actually be able to catalog the major threats to our planet. The discoveries weren't limited to the inner solar system. Rubin also looked outward beyond Neptune to the strange and mysterious realm of trans-Neptunian objects. These are icy bodies left over from the formation of the solar system, relics of a time 4.5 billion years ago when our planetary system was still assembling itself. In one observing campaign, Rubin detected roughly 380 of these distant worlds. 2 of them, designated 2025 LS2 and 2025 MX348, have orbits so stretched and elongated that at their farthest points, they reach about 1,000 times farther from the Sun than Earth is. Think about that distance for a moment. Earth orbits the Sun at 1 astronomical unit, the average distance between our planet and the star. These asteroids journey out to 1,000 astronomical units. That's the distance light takes nearly 6 weeks to traverse. They're so far from the Sun that the star becomes not a life-giving furnace, but merely a pale point of light in the sky. And there they are, these ancient frozen remnants tracing elliptical paths through the darkness, unknown to humanity until just months ago. The sheer speed at which Rubin is making these discoveries is itself a revelation. The observatory is alert and watching. Night after night, it sends out alerts to the world's astronomers, telling them what has changed in the sky since the last observation. In just one night recently, Rubin issued 800,000 astronomy alerts. 800,000. That's more than 100 alerts per second, continuously, from a single observatory. Eventually, as the system reaches full capacity, Rubin is expected to generate 10 million alerts in a single night. 10 million. What this means is that Rubin isn't just a telescope that takes pictures. It's a time-lapse camera for the universe. For 10 years straight, it will scan the entire southern sky, visible from Chile, recording the same regions over and over again, typically 3 to 4 nights apart. It will create a record of the universe in motion, and asteroids drifting across the solar system, stars exploding as supernovae, distant galaxies interacting and merging, everything changing over time. When the survey is complete, astronomers will have a decade-long movie of the cosmos, a moving picture of the dynamic universe in a way that has never been possible before. The scale of data Rubin will generate is almost incomprehensible. In its first year alone, this single observatory will produce more data than all of the optical telescopes in the history of astronomy combined. That's not hyperbole. That's the estimate from the project teams. Terabytes upon terabytes of information, flowing continuously from Chile to data centers around the world where computers and algorithms will sort through it all, finding the signals hidden in the noise, finding the needles in what is literally billions of haystacks. And Rubin will catch things in their earliest, most dramatic moments. When a star explodes as a supernova, that first burst of light is crucial for understanding what happened. If you miss the first days, you miss crucial information. But Rubin will catch them. Some of the earliest supernovae Rubin detected in its commissioning phase were at distances of 10 to 20 times farther than astronomers typically find them. The observatory is powerful enough to see stellar death across cosmic distances at the very instant of the explosion. Similarly, Rubin will see interstellar objects, rogue asteroids and comets that have escaped their home star systems and are wandering through space. The first known interstellar object, Oumuamua, was detected only because it happened to pass through the inner solar system. We caught a glimpse of it as it traveled by, but Rubin will find them far more frequently. It will track them, it will catalog them, it will make the rare commonplace. The implications stretch even further. One of the great mysteries of modern astronomy is whether a large, undiscovered planet exists somewhere beyond Neptune, a hypothetical world nicknamed Planet 9. It was first proposed in 2016 when astronomers noticed that distant trans-Neptunian objects all seemed to have orbits tilted in a similar way, as if something massive out there was shepherding them gravitationally. No one has ever seen Planet 9 with a telescope, but Rubin, with its combination of sensitivity and massive field of view, might finally reveal it. A direct image of Planet 9 would be one of the greatest discoveries in planetary science, and there's a real possibility that Rubin could deliver that image. Beyond the solar system, Rubin will revolutionize our understanding of dark matter and dark energy. These two substances make up about 95% of the universe, and we barely understand them at all. Dark matter doesn't emit light. Dark energy is even more. Constant, or whether it changes over time. These observations could resolve fundamental questions about the nature of reality. But standing here now, in mid-2026, with Rubin freshly online and just beginning its grand survey, what strikes most people is something simpler and more visceral. For most of human history, we lived beneath a static sky. Stars were eternal, unchanging, part of a fixed cosmic backdrop. Only in the last few centuries did we realize the universe. Observe the early universe and the late universe simultaneously, watching a cosmic history spanning 13 billion years. The Vera Rubin Observatory represents a fundamental shift in how humanity observes the cosmos. It shifts from asking, what are things, to asking, how do things change? It shifts from occasional discoveries to continuous surveillance. It transforms astronomy from a quiet, deliberate science to something more like real-time monitoring of a living universe. Far more populated, far stranger than we ever imagined. The dark skies above Chile are illuminating the cosmos like never before. And what we're learning is that we've been living in a cosmic storm all along. We just couldn't see it.